Hi everybody, this is our lecture on section 2.1. It's on matrix operations. Which we've discussed a little bit already in chapter 1, but here we did put it in more detail. So a matrix A is R by C when it has R rows and C columns. Sometimes we write A equal to, and then we do this kind of thing here, square bracket or a round bracket, round parentheses, Aij, just like that, where Aij refers to the element in row I, column J. So usually, we always list our rows first, columns second. So, for example, in a 2 by 3 matrix, it says row 1, column 1, row 2, column 1, row 1, column 2, row 1, column 3, row 2, column 2, row 2, column 3, like that. Okay? So just as how we were writing these things with systems of linear equations. Okay? Alright. Several operations go along with matrices. So first, matrix scalar multiplication. Given a matrix A, capital A, equal to bracket little aij, and a scalar R, we define the scalar R times matrix A to be the matrix whose entries are R, Aij. So every element of the matrix gets multiplied by that element, that scalar. So, for example, 2 times this matrix here, 1, 0, negative 1, 3, 0, negative 2. This is equal to 2, 6, 0, 0, minus 2, minus 4. Okay, simple little operation there. And just like with vectors, we had scalar multiplication of vectors, we have scalar multiplication of vectors, of matrices, and now we also have matrix addition, just like we had with vectors, vector addition. And, of course, you may, observe the point that, a vector really is just a matrix where the number of columns is 1. Okay, matrix addition. Given two matrices, of the same size, A equal to Aij and B equal to little bij, define A plus B to be equal to the matrix whose entries are the sums of the corresponding entries in A and B, just like we had with vectors. So, for example, we had minus 1, 1, 0, 2, minus 3, 0, so that's a 3 by 2 matrix plus another 3 by 2 matrix, 0, minus 2, 3, 5, 1, this is equal to, and you just add the corresponding entries. Minus 1 plus 0 is minus 1, 1 minus 2 is minus 1, 0 minus 2, 2 plus 3, 5, minus 3 plus 5, 2, and 1. Okay? And properties of addition and scalar multiplication of matrices. All the properties that you think hold would. Right? The addition of matrices is commutative. It's associative. Right? You can add three matrices in any order: B plus C first, then A, or A plus B first, and then C. Scalar multiplication distributes over addition of matrices. You have this kind of associativity with scalar multiplication. And addition of scalars distributes, well, over, so addition within scalars can be thought of as addition within matrices, like this. Of course, one needs to actually verify that all of these are correct, but, it's not something that's 100% necessary nor enlightening to do. So we'll just leave it at that these are all correct. All right. The third operation, which we don't have an analog with vectors, is matrix multiplication. Okay, so this one's a little more complicated than the other ones, but given M by N matrix A equal to Aij, and so not M by N again, N by P matrix B equal to Bij, like that. Define, okay, A times B, and here the order in which you multiply matters. Okay, A is M by N, and B is N by P. So the ends are lining up. Well, the ends follow each other. Okay, define matrix AB is equal to the matrix Cij to be the N by P matrix in which Cij is equal to, so row I of A and column J of B. So take row I, right? So row I, since A has n columns, row I looks like this: AI1, AI2, AIN. B has n rows. So you take the jth column, which has n entries, the jth column, which has n row entries in the matrix B. So this is B1J, and you multiply these, B2J, B3J, Nj. And then you take those products, and you add them. Okay, you take the ith row of A, the jth column of B, which have the same length, the same number of entries, and you multiply corresponding entries and then add that up. That is what the ith row j entry of the product is. So if you see it in action, it's not quite as mysterious as this, as it may sound. So let's take a 2 by 3 matrix. Okay, so minus 1, 0, 3, and so this is 2 by 3, 2 rows, 3 columns. Now let's take a 3 by 2 matrix, 3 rows, 2 columns. 2, 0, and 3 minus 1. Okay, so the result is going to be 2 by 2. Right? The 3's go away, and what's left over is 2 by 2. Alright, so the entry in the first row, first column. So take the first row, first column, and multiply the corresponding entries. So it's minus 1, and then 0 times minus 2, and then 3 times 3. Okay? Now we're going to do first row, second column. Right? First row, second column. Multiply the corresponding entries. Minus 2 plus 0, and then minus 3. And then the second row, first column, multiply the corresponding entries and add. 1 times 1 is 1, plus minus 2 times minus 2 is 4, plus 4, and then 3 times 2 is 6. And now take the second row, second column. 1 times 2 is 2, minus 2 times 0 is 0, and then 2 times minus 1 is minus 2. Alright, so that is the result. And if you just add those things up, we have 8 minus 5, 11, 0. Okay, so that's matrix multiplication. Another way to look at it is as follows. Right, if A is m by n and B is the matrix whose columns are B1 to BL, like that, is n by L. So we talked about a matrix times a vector back in chapter 1. So if you think of B as a collection of vectors, whose columns are a collection of vectors, then A times B is the matrix whose column vectors are AB1, ABL. Right, where that matrix multiplication is the one that we talked about in chapter 1. Okay? All right. So, some properties of matrix multiplication. So again, these properties have to be verified, but we'll just take them as they are. Okay, as true. We'll omit the proofs of them. So the first is that, well, as long as the multiplication is defined, right, you have associativity. You can take the product of B and C first and then multiply by A on the left, or take the product of A and B first and multiply by C on the right. Matrix multiplication and matrix addition, well, things distribute. 3b plus, they distribute on the left and they distribute on the right. Now, why am I making a big deal about distribution on the left as opposed to distribution on the right? You'll see in a moment. And then for some scalar r, the scalar product of r and matrix AB is the same as matrix RA times matrix B is the same as A times matrix RB. Okay, for any scalar R. The one thing that you might notice is missing is commutativity. Is not commutative in general. Okay, so if A and B are both n by n matrices, right, they have to be square matrices. So these are called square matrices. Then it might be that A times B is not equal to B times A. They might be the same. So they both have to be square in order for both of these to be defined, right? When you take n by n times n by n, right, these have to match up. So I can't do like 3 by 2 and 2 by 4 and then switch them where these match up and then switch them around. They have to be square matrices. Unless it's something like 3 by 2 and 2 by 3. Right? In that case, you can do it as well. But typically, it's used with square matrices. They're obviously different sizes, so they're not going to be the same. So if A and B are, but here it could be possible that they are the same when they're square. Right? If you had 3 by 2 times 2 by 3, right, the result is 3 by 3. Or if you had 2 by 3 times 3 by 2, the result is 2 by 2. Right? So, if this is A and B and this is B and A, obviously the products are different because they're completely different sized matrices. But when they're square, they have the same size. And it may be the case that A times B is equal to B times A. But in general, no. And you can take, pretty much any two reasonably complicated matrices, and they're not going to commute. So let's just say 1, 2, 3, negative 1. And let's multiply by 1, 1, 0, 1. Okay? So, for example, So if I do the product here, row 1, column 1 is 1 plus 0. Row 1, column 2 is 1 plus 2, so that's 3. Row 2, column 1 is 3 plus 0. And row 2, column 2 is 3 minus 1. Doing it the other way around, 1, 0, 1 times 1, 2, 3 minus 1. Row 1, column 1 is 1 plus 3 is 4. So already you know they're different. Right? Already you see that they're different because first row, first column are different entries. Okay, you can multiply out the whole thing if you like, but you'll see that we already know that they're going to be different. First row, second column, 2 minus 1 is 1. First row, or second row, first column, 3. And second row, second column, minus 1. Right? Not the same. Not that they can't be equal, they certainly can be. So let's do it this way. So this is an interesting matrix right here. So a matrix with 1s along the diagonal and 0s everywhere else. If I do the product, let's do it a little bit more generally. Let's make 3 by 3 matrices. And if you take the product, and I'll leave it up to you to do it, what you get is the same matrix back. And if you did it the other way, you get the same result. One, 2, 1, 3, minus 1, minus 1, 0, 2, 2. If you did the product again, in this order, right, A times B and B times A, you still get this same matrix back. So these are the same. Okay, this matrix is a special matrix called the identity. Okay, IN, so let IN be the n by n matrix that has 1s along the diagonal. 0, 0, 1. And zeros everywhere else. So IN is this matrix here. Right, you've got 1s along the diagonal and zeros everywhere else. Right, so for example, I4 is this 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Now, if A is any n by n matrix, then A times IN is equal to A, or is equal to IN times A is equal to just A. So there you do have commutativity with this identity matrix, and this identity matrix, it sort of takes the place of the number 1 in the real numbers with ordinary multiplication of real numbers. Okay? So that's a special matrix called the identity matrix. And the identity matrix is a special example of something a little more general called a diagonal matrix. An n by n matrix is called a diagonal matrix when A equal to Aij has Aij equal to 0 when I is not equal to j. So every entry off the main diagonal is 0. So for example, if we had a diagonal matrix, 3 by 3 matrix, there's one like that. And the product of a diagonal matrix and another 3 by 3 matrix, has a special has multiplication by diagonal matrix. Scales rows and columns. So for example, if I take that 3 by 3 matrix right there, so let's copy it. Come on. And I multiply by any other 3 by 3 matrix on the left, say. We'll multiply D on the left. A, B, C, D, E, F, G, H, I. Like that. Well, what's the product going to be? First row, first column is just A plus 0 plus 0. Then B plus 0 plus 0. C plus 0 plus 0. Next row, right, 0 minus D plus 0. 0 minus E plus 0. And then 0 minus E plus I. Or 0 minus F plus I. And then the last one is going to be 2G, 2H, 2I. So we took this matrix and we multiplied on the left by the diagonal matrix. And what happened is that row 1 gets multiplied by 1. Row 2 gets multiplied by negative 1. And row 3 of this matrix gets multiplied by 2. If you did it the other way around, then it does the same thing to columns. This product is going to be equal to, well, first column gets multiplied by 1, A, D, G. Second column gets multiplied by negative 1, minus B, minus E, minus H. And third column here gets multiplied by 2. 2C, 2F, 2I. Right, and you can check that out if you want. Let's do the third row. So the third row, first row, first column is G. First row, second column is minus H. And, no, not first row. Third row, first column is G plus 0 plus 0. G plus 0 plus 0. Third row, second column is 0 minus H plus 0. And third row, third column is 0 plus 0 plus 2i. So each row is, multiplied by 1 in the first column, minus 1 in the second column, 2 in the third column. So diagonal matrices are kind of neat, right? They give you this kind of action. Left multiplication by a diagonal matrix, it scales the rows of a similarly sized square matrix, and multiplied on the right, it scales columns. Okay, so they're pretty neat. One last thing in this section, the transpose of a matrix. Given an m by n matrix A, the transpose, a transpose is the n by m matrix whose ith row is the jth column, or the ith column of A. So you exchange rows and columns. Okay, so for example, if I had a 3 by 2 matrix, A, B, C, D, E, F, and I want to transpose that, then this gives me the 2 by 3 matrix. The first column of the transpose is the first row of the original matrix. So that's AB. Second column is CD. Third column is EF. Okay? And that's a kind of an important matrix, and we'll talk more about it later. And then some properties of transposes. Properties. One, well, A transpose clearly is the matrix A back again. A plus B, if you add them and then transpose, it's the same as transposing both and adding. 3, scalar times A transpose is the scalar multiple of A transposed. And then the last one, if you want to transpose a product, goes like that. AB transpose is B transpose A transpose. Okay, not A transpose B transpose. Okay, so I'll leave it to you to, well, we'll do an example like that in the exercises. Okay, that's all for this section.